So we have been talking about increasing atmospheric temperatures, how that affects ocean warming, the patterns where the heat goes down, and that ocean takes up more than 90% of the excess heat. But the heat is coming from the carbon dioxide increase and other greenhouse gases. So we also have to figure out what's happening to all that carbon dioxide. We said about 25% of the emissions go into the ocean. Right? We will see later on when we do carbon cycle that there are several sinks of carbon dioxide and comparing to several sources of carbon dioxide as well. One of the most direct impacts of carbon dioxide on the ocean is that CO2 is very easily soluble in water. So we already talked about the buffering effect in the ocean where CO2 can keep on getting dissolved into the water because it's getting moved into other compartments. If you just had CO2 plus H2O becoming H2CO3, you would soon saturate. You cannot put more CO2 anymore. It's like taking a cup of water and putting salt or sugar in it. At some point you cannot dissolve more if it gets saturated. But if the CO2 is H2CO3 is moving into HCO3 minus and H plus, and then CO3 minus minus and H plus, and CO3 minus minus is being used by these calcium carbonate forming shells and corals and so on, then you have this situation where you can dissolve more CO2 without saturating the water. So that's one idea you should remember. The other one is that what we talked about is pH, right? pH is the log scale of the concentration of H plus ion. So that determines the acidity of water or a solution. And 7 is pure water, and we said ocean is a little bit alkaline, so it's at 8.1, 8.2. And we said because of this buffering ability, it's been moving, it's been maintained. The ocean's average pH has been maintained for millions, tens of millions of years, maybe even a couple of 100 million years at that level. Obviously, when you go to 1000 ppm during the time of the dinosaurs, you would have had pH impacts. But nonetheless, as you keep increasing the CO2 concentration in the atmosphere, the reactions do not move fast enough to continue to maintain the buffering effect. That's one thing. We'll see what that means. The other thing, if you're living in the water and you are able to maintain calcium carbonate shells like corals or these coccoliths and others, that means the water is not dissolving this calcium carbonate. So it is supersaturated. It's like the glass of water we talked about. You've already dissolved enough salt, so putting more salt is not going to dissolve it, so salt can remain. The same thing happens here. So the calcium carbonate has to be saturated enough that they can maintain the calcium carbonate shells. But these calcium carbonate shells dissolve if you move the pH down towards more acidic waters. And that is the problem. Okay, so a lot of these beautiful calcium carbonate forming shells are threatened when pH decreases and acidity increases. That's the ocean acidification. So here is the reaction. We are combining now CO2, H2O, H2CO3, HCO3 minus, etc., and writing the net equation. You can go back and look at those three equations. CO2 plus H2O gives you H2CO3. H2CO3 goes into HCO3 minus and H plus, and HCO3 minus goes into CO3 minus minus and H plus, right? If you combine them, you get CO2 plus H2O plus CO3 minus minus plus 2HCO3 minus. So ocean is getting lots of carbon dioxide and calcium and carbonate ions from all the rivers. Okay, so the ocean is managing this buffering with this. So if you begin to pump too many CO2 molecules beyond the rate of this reaction, then you begin to lose CO3 minus minus, which is critical for calcifying animals like corals and coccoliths and other things. There are many that are relying on calcium carbonate being in saturation or carbonate ion being available. Okay, so this is another way to look at it. We are putting CO2. There are plants and animals which want to take down the CO2. Ocean has a CO2 exchange. We'll see a little bit later where the CO2 comes out and where it goes in. Actually, you can already use your knowledge of El Nino and the CO2 profile. How does the CO2 profile look? It's low at the surface. It increases with depth. There is upwelling in the East Pacific. If you upwell, you're going to bring more CO2. So then the waters are like opening a Coke can. If you increase the partial pressure of CO2 in the surface water, and if the partial pressure of the atmosphere is lower, then the CO2 is going to escape into the atmosphere. That's called outgassing, right? So there are places where there is outgassing happens, and there is places where the ocean takes up, or ocean uptake happens. So carbonic acid decreases carbonate, increases H+. That decreases the pH, moves it towards acidic waters, and that's what is ocean acidification. And loss of carbonate ions leads to fewer shells and other hard parts, because the water is not saturated, so they have difficulty growing and they begin to dissolve. So here is the evidence, putting again with the context of the Keeling curve. Here we are with the increasing CO2, already a little bit older, so we are above 415 here. But nonetheless, here is the average pH of the ocean, has already decreased by about 0.1. You think, what's the big deal? Remember, this is a log scale. And for calcium carbonate forming shells, it is a big deal because it matters. We will see another reaction later on that shows that as you increase the CO2, the pH drops and CO3 minus ions are lost. That is the crux of ocean acidification. So this is independent of the warming, because warming has other impacts on solubility, air-sea gas exchange, and so on. This is just CO2 dissolving in the ocean, creating acidification and negatively affecting corals and other calcifying animals.